This conference will now be recorded.
Hello everyone. We started terms used in volumetric analysis, but 2 to 3 terms are left that will be covered today, and after that there will be discussion related to stoichiometry and limiting reagent and related problems. Here we have formality. So formality, it is the number of formula mass in grams present per liter of the solution. Okay, so we have heard about molar mass, equivalent mass, but here you are seeing something new, which is formula mass. Okay, so we have to know first what is formula mass. So this formula mass in the unit of gram, when we express this in such a way, then number of this formula mass in grams that is present per liter of the solution, that is actually formality. Now formality is used only in some special cases. It is not like molality, normality or molarity, which is frequently used, but sometimes formality, this term is required. Fine. So remember, when molecular mass and formula mass, these two are same. So under that condition, formality is equal to molarity. So in that case, you do not need formality. Okay, but sometimes it happens when you dissolve any solute in solvent, there is some dimer formation, or that is association, or there may be some dissociation. So only in those cases we have to consider formality. Okay, and another point, just like molarity and normality, we have already seen in these two cases there is some temperature dependence. So that is also true for formality. Fine. So how to express it? It is weight of the solute in gram unit divided by formula weight. So this is actually the same thing that we do, remember, when we try to find out number of moles. So what we do, in case of calculation of number of moles, we take given weight divided by molar mass. In this way you can get moles. Similarly, when you divide given weight or given mass by formula weight of solute rather than molecular weight or molar mass, then you will get this number of formula mass in grams, and volume of solution in liter, that will be in the denominator, because per liter what is the number of formula mass in gram, that will give you formality. So we will solve a question here. After solving this question, your idea will be clear. Acetic acid, in case of acetic acid, when it is in benzene, okay, it forms dimer. So CH3COOH, two molecules together, it will make a molecule which is dimer, and it will behave as if it is a single molecule, and it happens in benzene solution. So suppose you have taken acetic acid in benzene and there is dimer formation, and what is the mass? It is 1.2 gram, which is basically the given mass or given weight of the solute, and final volume was made up to 1 liter using benzene. So there is presence of 1.2 liter gram of solute in, and the final volume is 1 liter. From this information we have to find what is molarity, what is formality. Now for this we have to know first what is the molar mass of CH3COOH. So CH3COOH, it is actually how many carbon atoms? It is C2. How many hydrogen? It is total 4 hydrogen. And how many oxygen? There are a total 2 oxygen. Okay, that means for carbon it will be 12 into 2. 12 into 2. So it will be 24. For hydrogen it is 4, and for oxygen it is 2 into 16. So in this way you can calculate what is the molecular weight. So you will see it is actually it is 24 for carbon, 4 for hydrogen, 32 for oxygen. Now it should be multiplied by 2 if you want to get the formula mass, because molar mass is 24 plus 4 plus 32, which is basically 60. But we need here the mass of dimer, because it behaves as a dimer in this solution. So you cannot consider molar mass, you have to consider formula mass. So that is why we are multiplying these values 60 with 2, and ultimately you are getting 120. So now the next step will be to find out number of formula mass. As it is mentioned in the first point, it is the number of formula mass in gram that is present in liter. So for that we will divide given mass by the formula mass. Given mass is 1.2 gram, which is already given in the question, and now you are dividing it by 120, which is the mass of diamond, and this is the number of formula mass. But remember, this is actually present in 1 liter. It is present in 1 liter. So that is why directly it is giving you the value formality. You don't have to do any further calculation. It is already mentioned in the question that the volume was made up to 1 liter. So this is the number of formula mass that is present in 1 liter. So that is why it will be our answer. That is 0.01 is the formality of this solution. After formality, the next one is mole fraction, and this is the last term we will discuss here, that is required in volumetric calculation. So how to do this? The mole fraction of any component in a solution. Any component in solution means, suppose you have a solution and there may be, normally we consider one solute, one solvent, but it may be more than one also, 3, 4 like this. So that is why the definition is in this way: the mole fraction of any component in a solution, that is actually the ratio of number of moles of that particular component for which you want to calculate mole fraction, and then it is divided by total number of moles of all the components. So suppose there are component A, component B, component C. Then if you want to know what is the mole fraction of component B, then what you will do? You have to take number of moles of B in numerator divided by number of moles of A plus B plus C. So in this, that is total number of moles of all the components. Similarly, if you want to get mole fraction of C, you first have to take number of moles of C in the numerator, and then in the denominator it is same, just like the previous one, total number of moles of all the components. So in this way you can get the mole fraction. So suppose we have a binary solution. Binary solution means there is only two components, A and B. So in that case, mole fraction of A, which is normally denoted by capital X, subscript is A, so it will be equal to Na. So what is Na? Na is the number of moles of A. And look at the denominator, it is Na plus Nb, that is number of moles of A plus number of moles of B, which is basically total number of moles of all the components. And here we have only two components, A and B, because it is binary solution. Then mole fraction of B, capital XB, same thing, that is in the denominator we have not changed anything, only this numerator is changed. Now it is number of moles of B. Okay, and you can easily understand from these two equations, equation number 1, equation number 2, that if you add these XA and XB, basically it will always be 1. Not just for binary, even if it is more than 2, A, B, C or A, B, C, D, it will always give you, that is if you add all the mole fraction of all the components, XA, XB, then XC, XD, whatever it is, it will always be 1. Fine. We have a question here. What is the mole fraction of a solute in 2.5 molar aqueous solution? So see, here it is small m, and small m means it is molality, capital M is molality. So here molality is given, which is 2.5. From this information you have to find what is the mole fraction. Okay, which solute, that is not given, but solvent is given, aqueous solution. Aqueous solution means you have to consider water here. So as molality is 2.5, from the definition of molality we can say that 2.5 moles of the solute is present in 1 kg of water, because it is aqueous solution. So you know what is solvent. It is 1 kg water, 1000 gram water, same thing. Now 2.5 moles, suppose solute is A and the solvent is B. Fine. So number of moles of solute Na, that is 2.5, which is already given. But it is present, that is 2.5 moles present in 1000 gram. So 1000 gram of water, it is actually how many moles of water that we have to know. And for that, what we will do, this is as if the given mass of solvent, in our case it is water, divided by molar mass of water. So formula H2O, for 2 hydrogen it is 2 and for oxygen it is 16. So 16 plus 2, it will be 18. So that is why 1000 is divided by 18, and these are the number of moles for water, 55.5 moles. So 2.5 moles of A present in 55.5 moles of B, which is water. So if you want to know the mole fraction of solute, you have to use this formula, Na divided by Na plus Nb. In our case, it is 2.5 divided by 2.5 plus 55.5, and ultimately this is the answer. So mole fraction of the solute is 0.043. Next, another problem. 100 ml of sodium phosphate. The formula is given, Na3PO4 solution. It contains 3.45 gram of sodium. Now, what is the amount of Na3PO4? That is not given, but the mass of sodium, that is only one element, that is given, which is 3.45. You have to find the molarity of the solution in this format. Fill in the gap, multiplied by 10 to the power minus 2. Some more informations are also given. Atomic masses of sodium. For oxygen, it is 16. For phosphorus, it is 31. So, Na3PO4. Per mole of Na3PO4, or you can say per molecule of Na3PO4, what is the number of Na? It is 3 atoms present. Okay. So first what we will do, we will try to see if we divide this given mass of sodium by the atomic mass of sodium, which is 23. You can get the number of moles of sodium, right? Given mass divided by molar mass. In this case, it is atomic mass because it is single mono atom. If you know the number of moles of sodium, you can easily find out what is the number of moles of Na3PO4, because per Na3PO4 there is total 3 sodium atoms. So if X is the number of moles of sodium, the number of moles of Na3PO4 will be 1x divided by 3. That is 1/3 of X. So that is the relationship. So first we will find out what is the number of moles of sodium, given mass divided by 23, and it is 0.15. And number of moles of Na3PO4, because if you compare Na and Na3PO4, then it is 1/3, right? So that is why 0.15, that is now divided by 3. So this is the number of moles of Na3PO4. Now this is present in 100 ml. So we can now say that 100 ml solution contains 0.05 sodium phosphate, but we need the number of moles of sodium phosphate that is present in 1000 ml or 1 liter. So it will be 10 times more. That means now it is 0.5. Just simply multiply 10 with 0.05. So this is the number of moles now present. But this is not your answer, because you have to arrange this answer in the format which is given in the question. So it is an integer type of problem. Now if you write 5, 0, then 10 to the power minus 2. So now it is matching with this format. So this should be the answer. Okay. So we need 10 to the minus 2. That means you have to move the decimal towards right hand side. So just shift this 2 digit, it will be 5. So answer is 50. Next one. 250 gram of D-glucose solution contains 10.8% of carbon by weight. So D-glucose, which is, if you consider the formula of glucose, it is C6H12O6. That means per glucose molecule, there is total 6 carbon atoms. So again, see, in the previous problem also you have seen that Na3PO4, that is the solute, but what is the mass is given in terms of sodium. So here also the mass is given in terms of carbon. So glucose, there are total 6 elements present: carbon, hydrogen, oxygen, but only the mass of carbon in the percentage form is given. From this information, we have to find the molarity of the solution is nearest to which of these value. So you can find some similarity with the previous problem, right? So D-glucose, first we'll see as percentage is given and total mass is given. This is the mass of the glucose. So 10.8% of 250, that will actually give you the weight of carbon. Once you know the weight of carbon, and if you divide it by the atomic mass of carbon, you will get number of moles of carbon. Once you know the number of moles of carbon, you can also calculate the number of moles of glucose. Just we have done it in the previous problem. Given percentage 10.8, so mass of carbon divided by mass of solution 10.8. So this is the percentage. If you multiply with 250, you will get mass of carbon, which is 27 gram. So this is the mass of carbon present in 250 gram of glucose. So divide it by 12. You will get number of moles of carbon. Given mass divided by atomic mass, because it is singular, 2.25. Now glucose, which is having formula C6H12O6. So you can see per formula 6 carbon atoms. So that is why if it is 1 mole of glucose, there will be 6 moles of carbon. So that is why 2.25, it should be multiplied by 1 by 6. 1 by 6 of 2.25 is actually the number of moles of glucose, which is 0.375. Okay. Now 250 gram, that is actually the mass of solution, but you have to find molarity. Remember the definition of molarity? It is the number of moles of solute present in 1000 gram. So we have to know 1000 gram solvent. Next step will be to find out what is the mass of solvent in which these moles of glucose present. Molar mass of glucose is 180. Okay, and this is the number of moles of glucose. We know given mass by molar mass, that will give you number of moles. But in our case, number of moles already there and molar mass is there. We just have to find what is the given mass of glucose. So 67.5. This is the mass of glucose that is present in 250 gram of solution. Now the next step is to find out the mass of solvent in 250. So mass of solvent plus mass of solute is equal to mass of solution. In this case, you know the mass of solution, you know the mass of solute. So if you subtract it, mass of solute, that is mass of glucose, from the mass of solution, which is 250, you will get the mass of solvent, which is 182.5. Now we can say that 182.5 gram of solvent, that is containing 0.375 moles of solute. But we should know what is the number of moles of glucose present in 1000 gram. So that is why 0.375 divided by 182.5, and then it should be multiplied by 1000. So this will give you value near about 2.05. So it is matching with which option? It is matching with second option. Okay. So in this way, we can find out what is the molarity of the solution. Read the question very carefully, whether it is asking molality or molarity, because if you somehow missed the actual term, that is molarity, obviously the answer will be completely different. So read it carefully. Okay. 100 gram of propane, which is 3 carbon propane, and it is alkane, CH3, CH2, CH2, completely reacted with 1000 gram of oxygen. So this is what type of reaction? It is combustion reaction. And in combustion reaction of hydrocarbon, products are carbon dioxide and water. Okay. In this case, it is also given the mole fraction, it is asking for mole fraction of carbon dioxide in the resulting mixture in this format, x into 10 to the power minus 2. You just have to find the value of x, which is integer. Nearest integer you have to take. So this is the integer type of problem. Atomic weight of hydrogen, carbon, oxygen, these are also given. Now, propane, CH3, CH2, CH2. There are total 3 carbon and there is total 8 hydrogen. So first we will calculate, as propane is basically this one, CH3, CH2, CH2. So total 3 carbon atoms. So it should be, if you want to know molar mass of propane, it should be 12 multiplied by 3. And as there are total 8 hydrogen, it is 8 into 2. So this is the molar mass of propane. Once you know the molar mass of propane, you can find out what is the number of moles of propane present in 100 gram. So number of moles of propane present in 100 gram, given mass divided by molar mass, it is 2.27. Okay. And also here 1000 gram of oxygen, because 100 gram of propane is reacting with 1000 gram of oxygen. And we know oxygenity is diatomic, O2. Per oxygen atom it is 16, so it will be 32. That is the molar mass of oxygen molecule. Similar, just same type of calculation, given mass 1000 divided by molar mass of oxygen, and it will give you the number of moles of oxygen, 31.25. So these informations now we have in our hand. Next is you have to write the balanced equation of combustion reaction. So this is propane C3H8. It will react with oxygen, and it is very easy to balance the equation. What you have to do, as it is combustion reaction, products will always be CO2 and H2. And look at the formula of propane, C3, that means total number of carbon, left hand side, right hand side, it will always be 3. So carbon dioxide, here this coefficient, it should be 3. And total number of hydrogen is 8 in the left hand side. So right hand side also it should be 8. So that is why before water you have to multiply it with 4. 4 is the coefficient. Now when you have done this, how many oxygens are there in the right hand side? 3 into 2, 6. And here 4 in 4. That means total 10 oxygen atoms must be present in left hand side. So that is, it is 5. So now you can balance in this way. And as we have already calculated the number of moles of, this is for propane 2.27, before reaction T equal to 0, and before reaction total moles of oxygen 31.25. Now as it is a mole ratio, see, from 1 mole of propane you will get 3 moles of CO2 and 4 moles of H2. So 2.27, if you multiply it with 3, you will get 6.81 moles of CO2. If you multiply 2.27 with 4, you will get 9.08 moles of water. So now you know what is the number of moles of CO2 produced and water produced, because it is a complete reaction. It is already mentioned in the question, complete reaction. So 2.27 moles of C3H8, it will completely react. But when it will do so, as the mole ratio of propane and oxygen, compare this, it is 1:5. That means per mole of C3H8, you need 5 moles of oxygen. So 2.27 moles of propane means 2.27, if you multiply it with 5, that is the required amount of oxygen. And if you do this, you will see it will be near about 10, because it is 2.27 into 5. So the number of moles of oxygen that is already available, all the moles are not required. Some amount will be remaining extra, and this extra amount is 19.9 mole. So this will be the calculation. Look at this left hand side. Number of moles of oxygen actually required 5 into 2.27. which is clear from the mole ratio. 1:5, 11.35. Now, number of moles of oxygen remaining, because we have some excess oxygen. So this is the remaining amount. Number of moles of CO2, 2.27 into 3, 6.81. And this is multiplied by 4, 9.08. So now we have all this information. Now why we are doing, we are calculating all the moles of product as well as excess starting material. The reason behind it is that in the question it is asking the mole fraction of carbon dioxide. Now after reaction, what are the species left? C3H8, it is completely, it has taken part in reaction completely, so it is 0. So ultimately after reaction, reaction is over, you have total 3 species. You have oxygen, excess, and you have 2 different products, CO2 and H2. So total 3 types of species are present. So you should know the mole fraction. If you want to find out the mole fraction of CO2, one of these 3 species, obviously you have to know the number of moles of all these 3 species. So that is why, see, now we know the number of moles of oxygen present extra after reaction, we know the number of moles of CO2, we know the number of moles of H2. So these 3 things will be required when you will be going to calculate mole fraction of CO2. So mole fraction of CO2 in the final reaction mixture, 6.68, which is the number of moles of carbon, divided by number of moles of oxygen, number of moles of CO2, and number of moles of water. So ultimately you are getting this value. But as you have to express it in the format x into 10 to the power minus 2. So as it is minus 2, you have to shift this decimal 2 digit, and now it is 19.02, which is our x. So you have to take the nearest integer. So that is why it is 19. Fine. Our next topic is stoichiometry. Just look at this picture. Here, if we consider chocolate chip cookie recipe, what we need? Suppose you want to prepare 12 cookies. So for that you need 1 cup flour, then 4 eggs, half cup sugar, okay, then butter, chocolates, etc. So these are the ingredients that you require. Total 5 ingredients are there, and their corresponding amounts that is also there. But suppose you just want to prepare 1 cookie. So from this first information, you can easily understand what should be the measurement of each of these 5 species that are required ingredient. So now everything you have to divide by 12. So 1 cup of flour, now it will be 1 by 12 cup of flour. Then eggs, it will be 4 divided by 12, which is 1 by 3. Half cup of sugar, now it will be 1 by 2, then divided by 12. That means it is now 1 by 24. 1 cup of butter, now it is 1 by 12 cup of butter, and half cup of these chocolate chips, now it is 1 by 24 cups of chocolate chips. Okay. So why we are discussing this? Because this basic thing that you are seeing here, that is actually similarly you have to follow when you will consider some reaction. Fine, because you can consider here the cookies that you are getting finally as if it is the analog of product, and all the 5 ingredients that are mentioned in the left hand side as if they are the starting material. Okay, so you have to adjust the starting material, that is there I'm talking about what should be the moles in balanced equation, that you can adjust by dividing all the species by the same number depending on how many moles of product you want to get. So here 12 moles of product as if so, but if you want to get just 1 mole of product, you accordingly you have to adjust the number of moles of all these ingredients. So a balanced chemical equation is analogous to a recipe for chocolate chip cookie. It shows that reactants, that is in this picture the reactants are basically ingredients. It shows that what reactants combine to form what products. Product is cookies. This numerical relationship, that is actually known as reaction stoichiometry, and because it is based on the term ancient Greek words stoichion, which means element, and metron means measure. So if you add these two terms, stoichiometry. So this stoichiometry will give you the numerical relationship between chemical quantities in a balanced chemical equation. Fine. So here we have this reaction. Methane is reacting with oxygen. It is again a combustion reaction. You are getting CO2 and H2O. So total carbon left hand side 1. So right hand side also it should be 1. So that is why it is only 1 CO2. Total hydrogen 4. So it should be 2 H2O. In the right hand side total oxygen 4. So that is why it is 2 O2 in the left hand side. Now look at this table. Here reactants are methane and oxygen. Products are CO2 and H2O. All are gaseous. Stoichiometric coefficient, that is the term that is present before each formula. It is 1 for methane. Look at the balanced equation, it is 1. It is 2 for oxygen. It is again 1 for CO2, again 2 for H2. So if you want to know their mole ratio of these 5 species, it is 1 is to 2, then again 1 is to 2, 1 to 1. If we express it in mass-mass relationship equal to number of moles multiplied by molar mass, because we know when you multiply number of moles for each species with their corresponding molar mass, you get the amount. It is the mass of that particular species you get. Here, as it is 1 mole of methane, and methane molar mass is 16, 1 carbon 12, 4 hydrogen 4. So it is 12 plus 4, 16. 16 is the molar mass of methane, and here 1 mole, so 1 mole multiplied by 16, it will be 16 gram. For oxygen, it is having molar mass 32, but total moles 2, so it is 64. Similar is the calculation for these two also. CO2 is the molar mass of CO2, 44 is the molar mass of CO2, 18 is the molar mass of water. Next, you can also express it, see, in terms of volume. So mass of reactants, mole into molar mass of reactants. So here these two are expressed just like before in terms of gram, but you can express these two in terms of liter. We know that 1 mole of any gas, it will always be 22.4 liter provided temperature is 273 Kelvin and pressure is 1 atmosphere. So in under this condition, 1 mole of CO2 means 22.4 liter of CO2, and 2 moles of H2O in gaseous form, it means 44, that is vapor form, 44.8 liter. And if we express all of them in terms of volume, so it will be like this. Fine. So stoichiometric calculation, as you can see here, stoichiometry is the quantitative relationship between reactants and products in a balanced chemical equation in terms of moles. The quantity of reactants and products can be expressed in terms of moles, as you have seen in the first row. Then we have also expressed it in terms of mass. You can also express it in terms of volume, provided they are in gaseous form. So we can express it in different ways. And remember, these 3 types of units, moles, then mass, or it may be volume, they are actually interconvertible. So if you want to convert mass, that is given mass, to number of moles, then you have to divide it by molar mass. Given mass by molar mass, you will get number of moles. If you want to move from number of moles to given mass, now you have to multiply number of moles by molar mass. So this is the relationship. And if the condition given 273 Kelvin and 1 atmosphere, then you can also convert number of moles to volume, just simply multiplying 22.4. And the reverse, from volume to moles, you have to now divide it by 22.4. That is the given volume, that should be divided by 22.4 liter, and you will get number of moles. So these are the relationship by which you can interconvert all these 3 units: mass, number of moles, and volume, provided the species are gaseous and they are under the condition 0 degrees centigrade, 273 Kelvin, and 1 atmosphere pressure. Our next topic is limiting reagent. Remember that problem, and that is 2 to 3 slides before, the problem that we have discussed, where propane is reacting with oxygen and some amount of oxygen is extra. Two starting materials are there, propane and oxygen. But among these two, all the propane it is consumed, but oxygen, it is some amount extra still present even after the reaction is complete. So it means here the limiting reagent is basically propane because it is completely consumed, and excess reagent is oxygen. Now look at this equation. Here we have total 4 hydrogen molecules and 6 oxygen atoms in terms of atoms, not O2. So you can also consider as if total 6 hydrogen atoms are present. Sorry, 8. 8 hydrogen, 3 oxygen. So from hydrogen and oxygen we are getting 3 water molecules. 1, 2, 3. So all the 3 oxygen atoms are consumed. But for formation of 3 moles of water, you just need total 6 hydrogen. But you have total 8 hydrogen. So 2 hydrogen atoms are still extra. So here what is the limiting reagent? Here limiting reagent LR is oxygen and excess reagent is ER, hydrogen. Okay. So if any reaction is carried out with stoichiometric quantities of reactants, then all the reactants will be converted into products. So if it is already some balanced equation and the reagents are also present following the same mole ratio as it is in balanced equation, then there is no question of limiting reagent or excess. Just required amount is present. For example, in this particular example, suppose instead of taking 8 hydrogen atoms, you have taken only 6 and you have taken 3. So there is no question of limiting. You are just simply following the stoichiometry present in balanced equation. Because when you want to prepare 3H2 molecule, you need 6 hydrogen atoms and 3 oxygen. But in practical, that is not the case always. Maybe you will have some reagent extra. It may be hydrogen extra or oxygen extra in this case. So if you follow the stoichiometric quantities just like balanced equation, it will, all of them will be completely consumed. Nothing will be remaining extra after reaction. But if a reaction is carried out using non-stoichiometric quantities of the reactants, the product yield will be determined by the reactant that is completely consumed. That means the product yield will be determined by the limiting reagent. In this case, oxygen. So as you have taken 3 oxygen atoms, you cannot get more than 3 H2O moles. So only maximum you can get 3 moles of water, not more than that. It is not possible. So here product yield is decided by the number of oxygen atoms, number of moles of oxygen atoms present. It limits the further reaction from taking place and is called limiting reagent, and the other reagent which are in excess, it will be called excess reagent. Here we are trying to prepare ammonia from hydrogen and nitrogen. And this is balanced equation, 3H2 plus nitrogen, 2 ammonia. Just compare both sides, number of hydrogen, both sides same, it is 6, number of nitrogen, both sides same, it is 2. Now when it is 3 hydrogen, it is 6 gram, and when it is 1 mole nitrogen, it is 28 gram. Fine. So the first equation, it is basically, there is no question of limiting reagent, it is absent. Because you are just following the balanced equation. You are just following the stoichiometry that is actually required. But in practice, it may not be always so. Now in the second case, if you see, nitrogen is same. It is still 1 mole, 28 gram. But now hydrogen amount is reduced. It is now 1.5 moles. That means half of the previous moles. So mass is also half, 3 gram only. Now the yield of the product, that will be decided by the limiting reagent, which is in this case hydrogen, and this is excess. reagent. So in the right hand side, you can see 14 gram remaining extra because from balanced equation, as you can see that the ratio of H2 and ammonia, it is basically 3:2, right? So when you have taken 1.5 moles of H2, this should be only 1 NH3, that is 3. Here the ratio is 3 and 2. Okay, so for 1 H2 it should be 1:2 by 3. Similarly, when it is 1.5, as if you are multiplying 1.5 with 2 by 3, and it will give you, that is only 1 ammonia. So you cannot get more than 1 mole of ammonia. It is not possible. So here yield of ammonia, that is actually decided by the limiting reagent, which is hydrogen. Okay. So 1.5 moles, we are getting only 1. So everything will be now half. That is 3 divided by 2, it is 1.5. So in the previous case, as you are getting 2 moles of ammonia, now it will be only 1 mole of ammonia. Fine. And out of 28 nitrogen, 28 gram, as only, that is 1 nitrogen atom is used, that means only 14 gram nitrogen is you have used. So that is why 14 gram will remain extra. So that is why it is excess reagent. Okay. Some problem. The minimum amount of oxygen in gram consumed per gram of reactant is for which reaction? Because total 4 different types of reactions are given in options A, B, C, D. Okay. So in all the reactions, one thing is common. Which is the common point? That oxygen is common reagent in all these reactions. And there is some other substrate present. In first case, it is propane, then phosphorus, then iron and magnesium. Okay. So you have to find that in which case per gram of reactant. By reactant, it means it will be propane for option A, P4 for option B, iron for C, Mg for D. So per gram of reactant, in which case minimum amount of oxygen consumed, that you have to choose as correct option. Atomic masses are given for all the elements present. Look at the first equation, C3H8. In one of the problem that we have discussed in today's video, here you have seen it is 44, which is the molar mass of C3H8. So it is not done again. Same thing, just you have to follow. So as the mole ratio is 1 mole reacting with 5 moles of O2. That means 44 gram of C3H8 is reacting with 5 into 32 gram of oxygen. So this is the mass of oxygen. You have to multiply 5 with the molar mass of oxygen, which is 32. So 44 gram is reacting with 5 into 32. That means 1 gram will react with this amount, which is 3.63 gram of oxygen. So for the first equation, you have already obtained the value of, that is the mass of oxygen consumed per gram of the reactant. That is per gram of C3H8. Same type of calculation you just have to do for the other 3 reactions also. So for P4, as there are total 5 phosphorus, and see your atomic mass is given 31, so 123. How you will get? It is 31 multiplied by 4. Okay. So it is 24. 124. So 124 gram of P4 is reacting with 5 into 32 gram of oxygen, because this is also 1:5 mole ratio. But you have to find 1 gram of P4 reacting with how many grams of O2, which is 1.3. For the third one, here the mole ratio is 4 moles of Fe reacting with 3 moles of O2. So 4 into 56, because atomic mass of iron 56, 4 into 56 of iron reacting with 3 into 32. that is 96 gram of oxygen. 1 gram of Fe should react with 96 divided by 40 into 56, which is 0.43. And for the last one, here the mole ratio is 2:1, 2 mg plus O2. So 2 into 24, because magnesium is 24 atomic mass, reacting with 32 gram of oxygen, because only 1 mole of oxygen is present in the balanced equation. All these reactions that you are seeing, it is balanced. Otherwise, you cannot do this type of calculation, right? And 1 gram of Mg will react with 32 by 48, 0.667. So in all these 4 calculations that you have done, you just have to see in which case it is the minimum. See, this is the minimum, 0.43. Just compare all these values. 0.43 is the minimum. So that is why correct option should be option C. A chloro compound A, it forms aldehyde when we are doing ozonolysis. It forms aldehyde on ozonolysis followed by hydrolysis. That means this chloro compound A, there must be some CC double bond present. Then only ozonolysis is possible. Okay. When vaporized completely, 1.53 gram of this chloro compound A, it gives 448 ml of vapor at STP. So this second information is very important, because from this information you can find out what is the number of moles of A. Because when volume is given in STP and dividing it by 22.4 liter or 22400 ml, you can find out what is the number of moles. And as there is mass, given mass of species A is given, 1.52 is the given mass, and you also know the number of moles, you can easily find out the mass of this chloro compound. From these two information, you have to find what is the number of carbon atoms present in a single molecule of this compound A. So we will use this second information, that is number 2. This information we will use first. 448 ml is the volume given for this A species at STP. But if you divide it by 22400 ml, don't use 22.4 liter, because here unit is ml. Convert 22.4 to ml, which is 22400 ml, then use this here. So it is 0.02 moles of A. Now this is the given mass. So given mass, when you divide by number of moles, you will get the mass of A actually present. Okay, sorry, it is just forget about what I am saying. This, by mistake I have said. I'm trying to say, if given mass is divided by total number of moles, you get molar mass. So this is actually the molar mass of A. So now you know the molar mass, and you have to use this first information. The first information is saying that it is giving you aldehyde after ozonolysis and hydrolysis. That means one side of CC double bond, there must be forms aldehyde. There must be, I'm just considering simple alkyl group that is possible, which is basically CH3 and H. And other side, if I keep it minimum, one chlorine must be present. And here, as I'm following as minimum molar mass as possible, I'm just placing a hydrogen. Now, here, if we do ozonolysis, what we will get? There will be this CC double bond cleavage. So from one side, you will get CH3COH, which is acetaldehyde. From the other side, you can get HCOCl. But if you look at this molecule, it is basically C3H5. So just you have to follow trial and error, because actual structure you do not know. You just have to use this information. You know the information, it is giving you aldehyde and it has molar mass 76.5, and one chlorine is also present because it is chloro compound. So this is a minimum formula. It cannot be more minimum than this. Now C3H5Cl, if you consider its molar mass, it is 3 into 12. That means it is 336 for carbon, 5 for hydrogen, and for chlorine it is 35.5. Now if you add all these, basically you will get 76.5, which is completely matching with this. So this should be the correct formula. But we have to find the number of carbon atoms. So how many carbon atoms are present? Total 3. So answer should be 3. Next problem. Mostly the question that we'll get in exam from this particular chapter, that is some basic concepts of chemistry, it will be mostly numerical. So that is why I'm trying to solve as many questions as possible. The density of sodium hydroxide solution, that is given 1.2 gram per centimeter cube. The molality of this solution dash and then small m, because molality is expressed by small m. You have to round it off to nearest integer, and some more information are there. Atomic masses for these elements are given. Density of water is also given. So density of NaOH 1.2 gram per centimeter cube. It means if you take 1 cm cube solution, the corresponding mass will be 1.2 gram. Fine. Or if I say 1 ml, that is also fine, because ml and centimeter cube both are same. So you can write mass of 1 ml or mass of 1 centimeter cube solution. The corresponding mass is 1.2 gram. But we need what is the mass of 1 liter or 1000 cm cube or 1000 ml. All these are same. It should be 1200, because for 1 ml if it is 1.2, for 1000 ml it should be multiplied by 1000. So now it is giving you the mass of solution, which is 1200 gram. But as we have to find molality, we need what is the mass of solvent. Okay. So mass of water, which is solvent, in 1000 ml solution. Now you can say that when we are considering solution, there is both a presence of both NaOH as well as water. But actually see, here amount of NaOH compared to water is very, very less. So you just have to neglect, and it is solid also. So the corresponding volume of this solid, it is actually very, very less. So that is why we can write it as if mass of water in 1000 ml solution, it is actually same, that is 100 gram, because density of water given 1 gram per cm cube. And here we are neglecting the volume of NaOH. We are considering as if in 1000 ml only water is present. So you just have to consider this, because the volume that you are getting from NaOH, that is actually very less. So you can ignore it. And this assumption we have to do, otherwise we cannot solve this question. So mass of water in 1000 ml solution, it is 1000 gram. Now once you know this, that is the mass of solvent, now you know it. So if you subtract it from 1200, you can get the mass of solute, which is NaOH. So this is the mass of solute. Now you know the mass of solute, but you have to know the number of moles of solute. So for that, you should know what is the molar mass of NaOH. So see, here atomic mass of sodium given 23, for oxygen 16, for 1 hydrogen it is 1. So this is the molar mass. So number of moles of NaOH present in 200 gram, it will be given mass by molar mass, which is 5. So 5 is the number of moles of NaOH which is present in 1000 gram solvent, because here see, out of 1200 gram, 200 is the mass of solute. So rest of the part is 1000 gram solvent. So in 1000 gram solvent, you have 5 moles of NaOH, and that is the definition of molarity, the number of moles of solute present in 1000 gram solvent. So that is why the answer should be 5. Okay. Ten ml of 0.05 molar KMnO4 solution was consumed in a titration with 10.0 ml of given oxalic acid dihydrate. This dihydrate term is very important. Don't miss it. Why it is so, you will get to know after some time. You have to find the strength of given oxalic acid solution in this format, round off to nearest integer. So this is a redox reaction. KMnO4 is oxidizing agent, oxalic acid is reducing agent. Fine. Now in acidic medium, KMnO4, it behaves in this way because it depends whether you have taken acidic medium, basic medium. So when it is acidic medium, MnO4 minus is converted to Mn2 plus. And you just have to balance oxygen atoms. So 4 oxygen left hand side, it will be 4H2 in the right hand side. When it is 4H2, it should be 8H plus. And you have to add H in terms of H plus because it is acidic medium. Next step is to balance charge. You have to add 5 electron left hand side. Then only you will see both sides same charge. So in the left hand side, 1 negative charge, 5 electron, total 6 negative charge, and 8H plus. That means 2 positive charge, and in the right hand side also it is 2 positive charge. So number of electrons involved, total 5. This is important. And when it is oxalic acid, oxalic acid is actually, we have just taken the ion. That is the important part, C2O4 2 minus. If you consider the full formula, it is H2C2O4, but we have just removed H, and C2O4 2 minus, it will be converted to CO2. So this is basically a reduction because it is supplying electron. So we just have added 2 electron to balance charge both sides and 2 CO2 to balance carbon and oxygen. Now, this is actually the formula of oxalic acid dihydrate. You also have to consider this. And remember, from this, if you write the formula, it is C2H6O6. And if you follow this formula, that is considering dihydrate, it will be 24 plus 6 plus 96 for oxygen. So molar mass will be 126. So why I am calculating, you will just need it after some time. Now for any reaction, that is the reaction between KMnO4 and C2O4, balanced equation, even if you do not write it is fine. You don't need to do that. But this is important information. N equivalent of KMnO4 is always equal to N equivalent of H2C2O4 in terms of equivalent, not in terms of mole. Now, this is actually the number of moles of KMnO4, and this is the number of moles of oxalic acid dihydrate, because 1000 ml contains 0.05 moles. So when you do this calculation, that is 1000 ml contains 0.05, so 10 ml should contain 10 into 0.05 by 1000. Similarly, you do not know what is the molarity of oxalic acid, so we have mentioned capital M, but same type of equation. But this part is number of moles. When you divide it by 5, it will give you in terms of equivalent. So from this equation, you can get the value of M, which is 0.125. So this is the molarity. So this number of moles present in 10 ml, right? So from moles, if you convert it to gram by multiplying molar mass, this is the mass of oxalic acid dihydrate present in 1 liter, but it is asking the strength of given oxalic acid solution in this format, and the unit should be gram per liter, not moles per liter. Be very careful about the unit, because if you consider moles per liter, answer will be different. This is the number of moles present in 1000 ml, but this is not answer. Answer is in terms of gram. So that is why this 126 value that I have calculated here, that step you have to do. So you are multiplying number of moles present in 1 liter with molar mass, it will give you this value. But as there is 10 to the minus 7, you just have to shift this decimal 2 digit, and ultimately the answer is 1575. So in this way you have to solve it. We are at the end of the session. Thank you for listening.